All right, so this is the last actual lesson of new stuff from this unit. So from here on out, we've got some activities in labs. Um, Apologize that I haven't been able to be at school, but things do happen. We will be looking later this week, just so you all know, at a little bit of a quick research project. And then also there will be a lab happening, and we're looking at our next unit test coming up very quickly. All right, that all being said, electrolysis is one of the applications of electrolytic cells. One of the things we can do with electrolysis is break things like water. Water is one example, but there's other examples as well. If I were to take, now water is one that we will do a demonstration of in class, because we can make it into oxygen gas and hydrogen gas, neither of which is exceptionally dangerous. On the other hand, if we were to do this with something like sodium chloride, number one, we would have to not have it in an aqueous environment. We could take sodium chloride, so table salt, melt it, so give or take 900 degrees Celsius, and at that point we would have ions. And what we would also see is that yes, indeed, we could make this into sodium metal and chlorine gas, neither of which is exceptionally, classroom safety and friendly. So we're going to leave all kinds of other things alone. But I just wanted to point that out because if we were to go back in time to the 1800s, one guy of note is Sir Humphrey Davy. He discovered or isolated, I guess I should say, several elements in their pure form using electrolysis. All right. So coming back to this, water can be broken down into its elements using an electrolytic cell. Pure water is not a good conductor of electricity. Very often we'll put a non-reactive ionic compound into it. A common one is sodium sulfate. Now, if we don't have that in any kind of an acidic solution, sulfate by itself is a spectator. Sodium is such a weak oxidizing agent, it is not going to be the reacting part. So it doesn't actually take part in the reaction, but it does speed it up because it allows the solution to more easily conduct electricity. Usually in this case, the reaction is going to use inert electrodes. So think platinum or carbon, because they're not going to participate in the reaction. So the question that you could ask in terms of, that I could ask you, that you could answer maybe already in terms of electrolysis is this. Calculate the voltage required under standard conditions to separate water into its elements in an electrolytic cell, given that sodium sulfate is in solution to allow for easy conduction of electricity. List the strongest reducing agent and strongest oxidizing agents to get started. So in this case here, this is actually pretty easy. We have water is obviously present. I can, put down that yes, there are sodium ions. Yes, there are sulfate ions. But as I already said, sulfate ions, if we have no H pluses present, they don't react. Sodium ions, we do have a very weak reducing agent there. Sorry, my apologies. Really weak oxidizing agent. They are, if you look in your chart, sodium ions are fifth from the bottom. And water will act as an oxidizing agent. Water will also act as a reducing agent. And guess what? My strongest oxidizing agent and my strongest reducing agent are water. All right. So I find, first of all, the reduction half reaction for the oxidizing agent. So for water as my oxidizing agent. I find this one where water is on the left, and it's got to be water by itself. And in this case, it is negative 0.83. So this is the 2H2Os plus 2 electrons are going to give us hydrogen gas and some hydroxide. Two OH minuses. We're going to pretend that that says AQ, not just some kind of a weird parenthetical comma or something goofy like that. And so now this is my strongest oxidizing agent. This is reduction, right? Because we're gaining electrons. So this is happening at the cathode. So we'll see next to it just to remind myself of that. Now, as my reducing agent, I find water on the right-hand side. Once again, we have 2H2Os. Oops. And my 2H2Os that are liquids are going to go to sorry, this is the one that I always look at and then lose. This is going to give me 4 electrons and 4 H pluses. And oxygen gas. All right. So now a couple interesting things that we have to look at here. First interesting thing is, well, we have 4 electrons in this second one in the oxidation half reaction. Again, that happens at the anode. 4 electrons there and only 2 at the cathode, so we need to multiply everything here by 2 so that my electrons balance. Right, I'll just change the color. So it means I have 4 H2Os and 4 electrons and 2 hydrogen gases and 4 OHs. All right, now I add these 2 reactions together. My electrons cancel. I have 4 plus 2 is 6 H2Os on the left side. And I'll write it out. You'll normally not write it quite the way I'm going to do it, but I'll show all my work just so you can see what goes on here. So I have 6 H2Os on the left. These are, of course, liquid. And these are going to form 2 H2 gases plus an oxygen gas. And then we might think, oh, this is interesting. We have some hydroxides and we have H pluses. And then we might start to think, oh no, do I need to deal with sulfate now because H pluses and sulfates? But the answer is no, because we have 4 H pluses, yes. We also have 4 OH minuses, and guess what? H plus and OH minus react very quickly to give us waters. And so this is going to make 4 HOHs, which are basically like 4 waters or H2Os. Which means, suddenly my writing got messier, I apologize. Which means I've got 4 waters on this side, 6 on this side. These all go away. I'm left with 2 here. Now, I add those reactions, but to find the electrode potential, what we're going to have to look at, we need to take our cathode half reaction, the reduction half reaction for the cathode, minus the reduction half reaction for the anode. And so if I want to find out E cell here, and in terms of minimum voltage, is going to be cathode minus anode. And so my cathode reaction is going to be negative 0.83. Remember that I don't have, even though I multiplied the equation by 2, I do not multiply the voltage by 2, or 3, or whatever I'm going to multiply by. In this case, it's 2, though. And then I take my anode half reaction, but I write it as a reduction for the reduction potential, so I'm not flipping signs or anything like that. That's going to be 1.23. So it's going to be negative 0.83. So again, my formula is, you can probably write this underneath and neater. I'm just writing with a mouse on a screen. So E cell is going to equal the cathode reaction minus the ER. The R again here is just showing me that this is the reduction potential. So I'm not flipping signs, and this is the anode one. So it's going to be this negative 0.83. Volts, a minus 1.23 volts. And this gives us negative 2.06 volts. Lovely. So this tells me I need at least 2.6 volts to make this reaction proceed. Now, I can make that reaction happen a bit more easily if I use sulfuric acid rather than sodium sulfate. All right, so again, list what I've got present. I have H2O. H2O can be an oxidizing agent. Can also be a reducing agent. I have H pluses. And I have sulfate 2 minuses. And I know that together these things are an oxidizing agent. I also know that by itself hydrogen ions are an oxidizing agent. And so I go looking and I decide and determine that indeed, yes, my strongest oxidizing agent is the combination of hydrogen ions and sulfates. And if I look for my strongest reducing agent, is going to be water. Now, one of the things you should immediately see here is that compared to what we just looked at, so if I compare this H plus and sulfate as an oxidizing agent to just H2O water, this combination is definitely a stronger oxidizing agent. Now, it is not a strong enough oxidizing agent that it will spontaneously react with water. But I set up here more easily. Let's calculate the voltage for this one here. Now, if I know my strongest oxidizing agent is H plus and SO4 2 minus, now I can write this out, but in this case, is the question asking me to find out the overall net reaction? No, it's not. So if I want to do this the short way, I look and I say, okay, strongest oxidizing agents, that means it is reduced, which means This is at the cathode, which means if I look at my formula again, E cell equals E cathode minus E anode. Now I didn't write down the little r, so I can do that as well. Again, that's just reminding me that this is the reduction potential, which means it's the voltage or the electrical potential as written in your data book. So look at the cathode one first. And for the cathode one, this is positive 0.17. And for my anode one, it is water, and it's where water is on the right, so that's 1.23. And 0.17 minus 1.23 should, if I can math in my head, give us negative 1.06, but let's just double check that. It is indeed negative 1.06. So my cell potential here is negative 1.06 volts. And so, yeah, you can see adding H2SO4 is going to make this reaction proceed a little bit more quickly. One of the things about that reaction, if we were to go through the whole thing, though, we would see instead of that reaction taking place that we looked at before, where we're getting both hydrogen and oxygen, in this case here, given that our strongest oxidizing agent is the sulfate and the hydrogen ions, what we're going to see is we're not actually going to get the hydrogen gas, but we will get the oxygen gas. So if we're looking to get oxygen gas and hydrogen gas, we would need to use a different acid than sulfuric acid. Okay. Anyways, this is just calculating how much energy is required to make this thing proceed. Now, you could ask, well, what if we'd used hydrogen ions? Well, if we used hydrogen ions, you can see that's right at 0.00. In that case, we would end up with negative 1.23 volts required. And if you want to think about it, these reactions typically are lazy, which would mean that if they are lazy, we're not going to see all kinds of competing reactions happen. What we will see is the one with the lowest voltage will happen, right? The strongest oxidizing agent. If we were looking, if we had a different acid, so no sulfate present, just the H pluses, we'll still get H2, but now we're no longer actually doing electrolysis of water. All right, moving on. Electroplating. So another commercial use of electrolysis is electroplating. So what we can do is we take a relatively inexpensive metal like steel or copper, and we can coat it with a layer of a more expensive metal like silver or gold, or even get into some of the really weird kind of ones with rhenium or osmium. You can also have metals that have other desirable qualities such as conductance, strength, or corrosion resistance, and we can plate them onto other metals. And so in the case of this, whatever we're wanting to do here, the metal or object to be coated, we set it up as the cathode of the electrolytic cell. And the ions of the metal that will be deposited onto the cathode are then present in the electrolyte. We will supply the minimum voltage, and that's going to allow the reaction to proceed, and it causes the desired metal to be plated onto the cathode. Obviously, voltage greater than the minimum can allow the reaction to proceed more quickly. If you want to plate an iron object with zinc, why would we want to do that? Well, this is something that we're going to talk about later this week, but the zinc essentially acts in this case as a sacrificial anode and prevents the iron from rusting. So we've got two different metals in that case. We have both zinc and we have iron. And if we look on our table, we find out that zinc is below iron, which means in any kind of a situation where a spontaneous reaction is going to occur, instead of the iron, let's say it's our nail, starting to rust and react, the zinc is oxidized. But the zinc is not then deteriorating the strength of the nail, which means if we use zinc-coated stuff, so galvanizing things, this is the idea of galvanizing, is coating them with zinc. One way to do that is this way of electrogalvanizing, where we use electrolysis or electroplating to plate the zinc on there. All right, so let's look at the example here. If you want to plate an iron object with zinc, cathode would need to be the iron. The anode would generally be some kind of an inert material, and the electrolyte would be some soluble iron compound in order to provide iron 2+ ions. So think iron 2 nitrate or something along those lines. And then we say, okay, calculate the minimum voltage required to plate silver onto a copper electrode, and I changed this example because otherwise it's exactly the same as the one in your book, and apparently did not change this part. So this should be saying we are going to plate not silver but zinc onto a iron electrode. And my apologies. You're going to have to go back and do a little bit of changing. We want a soluble zinc compound in order to provide Zn2+ ions. All right. So we're going to plate some zinc onto a iron electrode. All right, so we get started and we figure this out. We're going to have, now I'm not going to necessarily make you do this every time, but let's take a look at what we've got. Well, we have carbon as our inert anode. We're going to have zinc chloride as an aqueous zinc compound that gives us a source of Zn2+, and we are having an iron solid cathode. Note there's no salt bridge, we don't need one. We just have the two electrodes and they're sitting out here. Now, just a really quick look here, we can right away see zinc 2+ is our strongest oxidizing agent. Iron solid is our strongest reducing agent. Nothing is going to happen in terms of a reaction between the zinc 2+ and the iron. Neither of them, are the zinc or the chloride, will react with the carbon either. So in this case here, we've got it set up. Iron is our cathode, and we are going to set this up now, and we're going to say, okay, well, what do we have present here? So, because you look at this and you go, I don't know if I can do the whole question. Okay, think again. I have zinc 2 plus. I have solid iron. Now, the one thing I gotta just mention here, although I have the solid iron present, because it doesn't spontaneously react and it's going to be plated onto there, it's not going to take place in the reaction. So you might say, I want to have this here. You don't need it. And in fact, what we then need to look at is water is going to be our other, because it's aqueous, so this is our other thing that we have present. We also have Cl minus. And away we go. So my strongest oxidizing agent is indeed going to be zinc 2 plus. My strongest reducing agent is going to be water. Now, again, you might start to think, well, what about the iron? Well, the iron is not going to participate in the reaction because the iron is going to be the cathode, and the cathode is where reduction takes place. Iron's already reduced. We can't reduce this anymore. So we don't worry about iron being in there. Right? So iron is our cathode, and we look at our reactions. So I have zinc 2 plus. This is the reaction happening at the cathode. Zn2 plus aqueous plus 2 electrons are going to give us solid zinc. And my oxidation half reaction is going to be my 2 H2Os. This is the one that always hides on my table, giving me 4 electrons. Oops. 4 electrons and 4 hydrogen ions. And an oxygen gas. All right. Now, I can do a couple of things here. In this case here, it's just asking me to calculate the minimum voltage. And that's typically what you're going to have to see. So you need to recognize that the strongest oxidizing agent is going to be reduced, and that's going to happen at the cathode. And that the strongest reducing agent is going to be oxidized, and that's going to happen at the anode. It's always going to be cathode minus anode in terms of the potential. And so in this case here, if I look at the zinc reaction is negative 0.76. And if I look at the H2O reaction, that is positive 1.23. And if I take negative 0.76 minus 1.23, I end up with my minimum voltage. So my minimum voltage here is going to be negative 1.99 volt. Well, my E cell is going to be negative 1.99 volts. And that means that my minimum voltage I need to plate zinc onto an iron electrode is going to be 1.99 volts. All right, let's continue. Remember if more than one non-spontaneous reaction is possible, then the reaction requiring the least amount of voltage will proceed for as long as the reactants are present. This includes water if the electrolyte is present in an aqueous solution. Water must always be considered when determining the strongest oxidizing agent and the strongest reducing agent. So the question is, could chromium be plated onto aluminum using chromium 2 nitrate as a source of chromium 2 plus ions? So we got to look here and we say, okay, well, if I look at this here, I've got a couple things. I'm going to be using aluminum as my cathode, so it's not going to take part in the reaction. But I have chromium 2 plus ions. I have nitrate kicking around. It's not acidic, so that's not going to actually take part. And I have water kicking around. Now, water obviously can be both an Ra and an OA. Chromium 2 actually can act as both an OA and an Ra. And now we look at strongest and weakest and all those kind of fun things. So if I find chromium 2 plus, chromium 2 plus is going to be my strongest reducing agent. And then I look to see chromium 2 plus on the other side. And chromium 2 plus is not my strongest oxidizing agent. So guess what? My strongest oxidizing agent, in fact, is going to be water. Now, if I use chromium 2 plus as a reducing agent, I'm going to make that into chromium 3 plus. So I am not plating any chromium onto the aluminum. I guess I will change the color. I will generate some gas because I am going to reduce H2O. H2O is going to reduce and make me hydrogen gas. But I'm going to get hydrogen gas, I'm going to get hydroxide, and I'm going to get chromium 3 plus in this reaction, even if I use electrolysis. So we have to keep our eyes out for things like that. And again, if you're looking for how and why this makes sense, look at where all of these things are in relation to each other on your table. Again, we are looking for strongest oxidizing agent is near the top on the left side. Strongest reducing agent is closest to the bottom on the right-hand side. All right, so that's just a kind of a keep in the back of your mind kind of thing. Remember that water is there. All right, electrorefining. Okay, so this is actually very similar actually. You're going to use electrolysis to remove a desired metal from a sample which contains metal impurities. Okay, so in this case we would use the impure metal as the anode. Several of the metals present at the anode are oxidized, but the desired metal can be preferentially reduced at the cathode, which will allow it to be recovered. The remaining undesirable metals form a sludge that is often called anode mud, which drops to the bottom of the cell and then can be disposed of. There's a similar method called electrowinning, and it's going to involve recovering a desired metal from a molten or aqueous electrolyte through electrolysis. So instead of electrorefining, where we have a metal sample that we know is not perfectly pure, when we use electrowinning, we have either a liquid like molten metal, so really hot, or we've got an aqueous electrolyte and we want to actually get something out of it. So, for example, going back to the above question, if we had chromium 3 plus, we could use electrowinning to eventually turn that back into chromium solid, and then we could recover it. Right? If I have lead 2 plus kicking around in a liquid, I can prevent pollution and lead poisoning from all kinds of creatures by using electrowinning, and I can actually also get that lead back, and I can then use that for some kind of other industrial purpose. All right. And you would think, I'm in Chem 30, I should be able to know all there is to know, and I'm going to have to tell you that there's more to this world than you ever dreamed of in all your philosophies, my dear Horatio, at least to badly paraphrase Shakespeare. The chloride anomaly. Now, we can usually predict reactions using our strongest oxidizing agents and our strongest reducing agents in a redox table. You can add the half reactions, determine the cell potential, predict either spontaneity or required voltage. Sometimes this rule doesn't work, and there are exceptions. One exception is known as the chloride anomaly. All right, so let's take a look here, and in this case here, we are going to calculate the voltage required to produce oxygen gas and hydrogen gas in an electrolytic cell with aqueous sodium chloride. All right, so I take a look here. It's an aqueous cell, so I have H2O is present. I have sodium metal, ions, not metal, sodium ions present, and I have chloride ions present. Now, if I look here, this can be an oxidizing agent, so I suppose can this. Water can be a reducing agent, and so can chloride. Now, I look at this and I say, okay, well, my strongest reducing agent, as in closest to the bottom on the right-hand side, is water. So there's my SRA. Water also is my strongest oxidizing agent. And if this looks like something we've already done, you are correct, it is. I'm going to ask you to go back to your notes. I'll show you where. Whoops. Right here. And I'd like you to calculate the minimum voltage to produce hydrogen gas and oxygen gas in an electrolytic cell using aqueous sodium chloride. All right, it should be negative 2.06. All right, that's the long and the short of it. And then we can do the same kind of a deal, but we're looking to produce hydrogen gas, and chlorine gas. So in this case here, chloride would have to be my reducing agent, and water still is my oxidizing agent. And so if we're going to assume that chloride is my strongest reducing agent, SRA, and water is my SOA. What we're going to find out is that, of course, my oxidizing agent is reduced at the cathode. So this is my cathode half reaction. This is my anode half reaction. Cathode minus anode is going to be what we want. So if I look at my cathode, voltage is negative 0.76. And I look at my anode is going to be positive 1.36. E cell is going to be this number minus this number. So negative 0.76 minus 1.36 should be negative 2.12. So E cell is negative 2.12. Now, if I compare that to the previous example we worked of negative 2.06, which one should happen? Well, the one with the lower voltage. According to our rules, chlorine shouldn't form, but it does. In fact, if we were to do this experiment, we would create small amounts of chlorine gas. We shouldn't do this experiment because we don't like to make chlorine gas. It's the poisonousness and things like that. Now, why this happens is well beyond Chem 30. Has to do with the fact that oxygen gas should be produced, but oxygen gas requires extra energy before it forms. Chlorine gas shouldn't be produced, but it does not require as much energy as oxygen in order to form. And the reason that the table can't accurately predict these few reactions is it doesn't always take into account the energy required to form a specific gas. Now, this is not the only anomaly. The chloride anomaly is the one that you have to know about, and you have to know that even though chloride should not form chlorine gas, it does. So if you are going to use electrolysis on water, don't use chlorinated water, and don't use sodium chloride as your electrolyte. All right, moving along. Take a break and come back in 5 minutes. We will be talking almost like physics for a moment. All right, you're back from your break. A little bit of physics, because physics is fun. Not much, but a little bit. So, we need to look at Faraday's law and some electrical energy and how that combines with stoichiometry. It's all great fun. Now, anytime we have a movement of electrons, normally from reducing agent to oxidizing agent, right, the oxidizing agent is reduced, so it gains the electrons, and it takes those electrons from the reducing agent, or the things that are oxidized. It produces current, right? The movement of electrons is current. Now, current, the symbol is I, because, yeah, physics is weird that way. Let's use an I to measure something that, yeah, anyways, or to denote something that is no I in it at all. It's measured in amperes, so I is the symbol for current, measured in amperes, or amps, symbol is A. 1 ampere is equal to the movement of 1 coulomb of electrons per second. Now, coulomb is a measurement of charge, or if we wanted to look at this in terms of what's the formula here, we can look at this and say I, which is current, is equal to, excuse me, Q, or charge, divided by time. So Q is a measurement of the quantity of charge, and divided by time. That will give us current. Now, for anything Chem 30 wise, this formula is background information only. We will have to calculate current, but we will never have to. We should never have to calculate it using this particular formula. All right. Charge, which is, let's use a Q because we've already got an I going on. Charge, now I think they use a Q because it's quantity of charge. Quantity of charge, or charge, is equal to the product of current and time, which means that Q is equal to IT. And if we want to know, like, okay, lovely, charge of electrons. Let's think about electrons. Well, the Faraday constant, I should tell you a little bit about Michael Faraday. Michael Faraday was an interesting guy. He lived in the 1800s, or when he did most of his work. He had very little formal education, was pretty poor. Kind of a cool story for him. Even though he didn't have that formal education, he was apprenticed. His dad was a blacksmith. He was apprenticed to a bookbinder, and he read voraciously. He read pretty much everything that the binding shop printed, and because most of what the bookbinding, a lot of what they dealt with was sciency kinds of things. Now they called it at the time a natural philosophy. We would have called it probably physics or science, but he read on that thing, that subject, and eventually said, you know what, this is really interesting. And so he applied, he said, and so he started doing more reading on his own. He did some experiments on his own. He applied eventually and worked for Sir Humphrey Davy. Now, Sir Humphrey Davy was a fairly famous scientist and hired Michael Faraday on as a lab technician, as well as somebody to help him with experiments and demonstrations during lectures. All right, so this was the guy who was, cleaning up the messes, setting the stuff up. Technically, he knew how to do it. At least this is what Davy thought. But in reality, it was more than just a technical knowledge. He was an absolutely phenomenal experimenter. And those experiments then, because of all his reading, he understood the background, and he was able to do some pretty impressive calculations, especially given the time. One of the things he came up with is what we call the Faraday constant, and it gives us the charge of 1 mole of electrons. And the charge of 1 mole of electrons is 9.65 times 10 to the 4th coulombs per mole of electrons. That value, by the way, you do not have to remember. It is given to you in your data booklet on page 3. So if you're looking under the miscellaneous stuff, we've got like specific heat capacities, water autoionization constant or dissociation constant, which we'll get to yet. And then there's the Faraday constant, 9.65 times 10 to the 4th coulombs per mole of electrons. All right. Now, if we are given a specific charge, we could then find out how many moles of electrons are required for that charge. So N, moles. We've seen that before. Moles of electrons is equal to Q, the specific charge we have, divided by the Faraday constant. But because we know this relationship, I can replace that Q here with IT, and I can say NE is equal to I times T divided by F. So if I have current and time, and my data booklet gives me Faraday's constant, I can figure out number of electrons, and number of moles of electrons, I should say. And because I know number of moles of electrons, and I've done chemistry before, I can do stoichiometry. You should be happy about this, maybe? I'm not sure. The nice thing about this, when we're doing this kind of stoichiometry, we need half reactions only because we actually need to see how many moles of electrons are being moved around. So let's take a look at one of these. Actually, 2 of them, one on this page, one on the next, and then we'll get to work. Determine the mass of nickel produced in an electrolytic cell in 1 hour that has a current of 4.00 amps applied. Just a quick step away from this for a moment. The one thing that we're always assuming in these situations is that we have 4.00 amps. It is also meeting the minimum voltage for the electrolysis to occur. So you could imagine, of course, some kind of a question where it's asking you what's the minimum voltage given the setup that we have, and then find out if this many amps of current, how many grams of nickel, for example, are produced. So let's take a look. So we are plating nickel. electrolyzing nickel, electrowinning nickel, taking nickel out of an aqueous solution. So we have nickel 2 plus 2 electrons, giving us solid nickel. Now the nice thing here, again, there is my chemical reaction. It is already balanced. It's wonderful. So I can find out the number of electrons. So let's find out how many moles of electrons, given the current, the time, and everything else. Because once I find moles of electrons, I'm going to then use my mole ratio to find out how many moles of nickel are produced. Then I'm going to use the molar mass of nickel to find out the mass of nickel. Okay. So pretty typical stoichiometry. This one's sort of nicer, I think, because we don't have much balancing to do. We do have to be careful that this is a formula that you need to remember, or memorize. There's ways you can derive it using stuff your data book gives you, but that's, I find, generally a little bit harder than actually just remembering it. So, number one. Step one, we want to find out moles of electrons, and that's using this formula up here. So step one is going to be N equals IT over F. The one thing we didn't talk about is that time here, because current is coulombs per second, time also needs to be in seconds. So this is going to be 4.00 amps. I'm going to assume that this is exactly 1 hour. So this is 3,600 seconds. Right, 60 seconds per minute, 60 minutes per hour. And we divide this by Faraday's constant, 9.65 times 10 to the fourth coulombs per mole of electrons. And so we pump that into our calculator. Make sure you can actually do this. Actually put this into your calculator. And even though my 6 became funny and it looks like it's 36.00, it is not. It is 3,600. So 4 times 3,600 and then divide that by 9.65 times 10 to the fourth. Not negative fourth, though. And there we go. We end up with 0.14922 and so on moles. So I have 0.149 moles of electrons. All right. And now my step 2, so this was step 1. Step 2 is going to be use my mole ratio to find out the moles of nickel. So if we take a look here at step 2, I have 0.149 moles of electrons. Multiplied by my mole ratio of what I want divided by what I have. So 1 mole of nickel divided by 2 moles of electrons. So it's going to be my big number in the calculator, essentially divided by 2, or multiplied by 0.5, or times 1 and then divided by 2. So I have here 0.074611399. So dot dot dot. Leave that big number in my calculator, moles. That's my step 2. Step 3, I'm going to use my mole ratio. Sorry, not my mole ratio, my molar mass to go from moles of nickel to mass of nickel. And so step 3, I am looking at mass is equal to little n times big M, which is going to be 0.74. So that's that 0.0746, etc. number that's still in my calculator, multiplied by the molar mass of nickel metal, which you may or may not know off the top of your head is 58.69 according to my periodic table. 58.69 grams per mole. And my mass is going to then be equal to that number times 58.69. 4.378, so looking back, 3 sig digs, so 4.38 grams. Of nickel. All right. That's one kind is, find the mass. Here's the other kind here. How long, so find the time, does an electrolytic cell with a current of 8.50 amps need to run in order to produce 10.0 grams of cobalt metal? So we look on our chart to find out cobalt metal. What is cobalt metal coming from? And it is coming indeed from cobalt 2+. And so we look at our reduction half reaction and we can say, oh, good, cobalt 2+ and 2 electrons gives me cobalt solid. Now in this case, I know the mass of my cobalt is 10 grams, 10.0 grams. I can use my periodic table to find the molar mass. And again, my overall strategy, I want to go from cobalt solid, eventually down to moles. I'm going to use my mole ratio to find out moles of electrons. And then I'm going to use my formula, N equals IT over F. So Fn over I will give me the time. Right. So again, my step 1 is what I'm kind of working on right here. Cobalt metal has a molar mass of 58.93 grams per mole. And so N is equal to little m over big M. This is supposed to be a little m. It keeps just getting bigger. 10 divided by 58.93 is going to give us 0.16969285559 and so on. So I'm going to leave the big number in my calculator here, 0.169 moles. Right? Now I'm going to multiply that by my mole ratio to get to moles of electrons. So moles of electrons is going to equal, let's do this the other way around. So again, I start with my 0.169 and so on moles of cobalt. Multiply that by 2 moles of electrons per 1 mole of cobalt. And take that number in my calculator, essentially multiply it by 2, and then divide by 1 if I really want to. That's going to be 0.339 and so on moles of electrons. Oh, that's, sorry, my mouse is struggling here. All right, and at this point here, I will use my formula, remembering that N equals IT over F. I want to solve for time. And so Fn over I is equal to T. And this is again going to give me time in seconds. So it's going to be my 9.65 times 10 to the fourth. Coulombs per mole of electrons multiplied by 0.339 and so on moles of electrons. And I'm going to divide that by my current, which in this case was 8.5 amps. And my time is going to be equal to, I punched that all into my calculator, 3,853 seconds. And 0.02 and so on. I have 3 sig digs here, so time is going to be equal to 3.85 times 10 to the 3 seconds. All right, and at this point, you're going to have some questions out of your snapbook. I will be back tomorrow, and we will go from there. Thank you, everybody.